This lesson is about alpha blending, and let me show you the program for this lesson. Actually, it's the same spinning cube, the same program that we've seen in a previous lesson. Or is it? Actually, no, it's a different program. I was just trying to trick you. Because if we go down here and we change this constant from 1 to 0.6, and then we run the program, you'll see that actually what we have in this program is a transparent spinning cube. So it's a different program. And that's what alpha blending allows us to do. It allows us to have transparent objects. Each transparent object has a particular alpha value indicating the opacity of the object. So this alpha value of 0.6 indicates that the faces of the cube are 60% opaque and 40% transparent. And what we're going to do is we'll draw all of the faces of the cube from back to front. And each time we draw a face, it'll go through the pixels of the face, and for each pixel, it'll sort of average it onto the pixel that was already there. So when we draw the farthest back face, we'll take each pixel and we'll take 60% of that pixel and 40% of the pixel that was already there, which happens to be black. And what I mean by this is the red component of the resulting pixel will be equal to 0.4 times the red component of the old pixel plus 0.6 times the red component of the pixel that we're drawing on top of it. And it's important that we draw the faces from back to front. Before, we didn't really care about what order we drew them in, but when we're using alpha blending, it's important to draw them in order. Basically, we're just simulating how lighting would work in the real world, the way that light would pass through the back and come through to the front before it reaches the eye. So it has to be in the right order. And let's take a look at some of the code now. First of all, we have a few constants. We have pi, which I'm just going to make this a little longer just to show off my nerdiness. But anyway, I know a ridiculous number of digits of pi, but that's kind of a side point. So then we have this constant right here, the length of each side of the cube, and we have our alpha component. And we're going to have a structure for storing each of the faces, for indicating where the face is. And what we're going to do is, instead of calling glRotateF, we're going to keep track of where the face is. We're going to directly specify each of the points. We're going to sort of rotate them manually instead of having glRotateF do it for us. And we're doing this because we need to know where all of the faces are if we want to sort them from back to front. So here we go. Our face structure is going to store 3 vectors that are perpendicular and all have a magnitude of 1. We have our out vector, which points outward from the face, so it's the same as the normal vector. And actually, we can use the out vector to figure out where the face is. The center of a face is just this out vector times box size over 2. We also have 2 other vectors, this up and right vectors, which just point in the directions of the edges of the face. So that's the face structure. We also have a structure for the cube, which stores all 6 faces of the cube. After that, we have a rotate function, which just rotates a particular vector about a given axis, a certain number of degrees. And this formula right here, I just found it online on MathWorld. Then we have a function for rotating a particular face, which all that has to do is rotate the up, right, and out vectors of the face. We also have a function for rotating a cube, which rotates each of the faces on the cube. After that is a function called initCube, which initializes the up, right, and out vectors of each face on the cube. So it just initializes our cube. Then we have a function called compareFaces, which we're going to use to sort the faces from farthest to closest. And the compareFaces function just takes 2 faces, and it determines whether the first is in back of the second face. And it does that by comparing the z-coordinates of the out vectors, which is basically just comparing the z-coordinates of the centers of the faces. And in general, comparing the z-coordinates of the centers of the faces, it doesn't necessarily work. because each pixel on a face has a different z-coordinate, the center doesn't necessarily matter that much. But it just so happens that in the case of a cube, if we sort the faces in this manner, using the z-coordinate of the center of the face, then when we draw them in that order, things will work out just fine. That'll end up drawing them from back to front. So we kind of got lucky in this case. Actually, there's sort of a tricky way to do drawings so that you don't have to sort the faces from back to front in this way, using backface culling. And I won't explain it right now. I'll explain it in a later lesson. For now, just know that it's out there. Then we have this function, face vertices, which figures out the 4 vertices of the quadrilateral for the face and stores them into this array, this v's array. Then we have a function, draw top face, which draws the top face of the cube. And first of all, it calls the face vertices function to figure out where the vertices are. And it uses this new function called glcolor4f to specify the color of the face. As I mentioned, each color, when we're using alpha blending, is going to have this new alpha component, indicating the opacity of the object. So we use this new glcolor4f object function call, and that'll take care of making our face look transparent. So that's the draw top face function. We also have functions for drawing the bottom face, the left face, the right face, the front face, and the back face. And we need separate functions for all of them because they all have different colors, or use color blending, or use textures, or whatever. And the back face is a textured face. You'll notice, by the way, that this call to glcolor4f will take care of making that transparent. So after that, we have a function called drawFace, which basically just takes a particular face. It figures out whether it's the top, bottom, left, right, front, or back face, and then calls the appropriate function to draw the face. So this function will make our life easier. Then we have our cube variable. We have the init rendering function, which has a couple of new things. It has GL-enable GL-blend, which turns on alpha blending, and it has a call to GL-blend-func. I mentioned earlier that whenever you draw a new pixel onto the screen, you're going to take, in this case, 60% of that new pixel plus 40% of the old pixel. Actually, you don't have to use that particular formula. You can use all kinds of weird formulas. With GL-blend-func, you just specify whatever formula you want to use. But if you want to just do standard transparency, this is what you want. GL-blend-func, GL-source-alpha, GL1 minus source-alpha. Then we have the draw scene function, where we're going to draw the face, draw the cube. The first thing we have to do is sort the faces from back to front. So we're going to use this faces vector to store all of the faces. And then we're going to call sort, which is a C++ function. It's in algorithm, so you just use number include algorithm to get the sort function. And the first 2 arguments are just faces.begin, faces.end. And the last argument is the function that we want to use to compare the faces, in order, what order we want to sort them in other words. And that's the compare faces function we saw earlier, which determines whether a face is in back of another face. And this sort function call will rearrange all of the elements in the faces vector so that they're sorted from back to front. Once they're sorted, we just call drawFace on all of the faces in sorted order. Then in our update function, we just have where we rotate the cube, and in our main function, we have a call to init cube, which initializes the cube. And anyway, that's basically how we can do alpha blending in OpenGL.